This is Bob Carpenter is going to do the next talk. He is currently a senior researcher at a research scientist at Flatiron Institute, which I probably butchered the pronunciation of that. And he holds a PhD from University of Edinburgh, and he is part of the STAN team working on the STAN probabilistic programming languages. And he's going to be talking about comprehensions, maps, and partial evaluation in differentiable programming. Go ahead, Martin.
Great, thank you very much. So I guess you already read out my title, so I can just jump straight into it. So what is differentiable probabilistic programming, at least in my conception? So we went through a long period in the beginning of STAN where people kept telling us we weren't a probabilistic programming language. And now I'm sort of happy the differentiable programming languages showed up, because that's really sort of how we're designed. But you can think of a differentiable programming language as something that lets you code a smooth function f and efficiently derive its gradients, Hessians, Jacobians, so forth. The cost is typically restrictions on the coding, in terms of the libraries that you can use, in terms of control flow, and examples and sort of historical order of how these things came out, I think, is back to ADL-C, things like Staccato, which STAN Math was based on, then TensorFlow, PyTorch. There's a lot of these libraries out there. Differentiable probabilistic programming, on the other hand, usually is of the form where the function is some kind of log posterior density up to a constant, right? And then we tack on some kind of sampling optimization, variational approximation, like Martin was just talking about. The first one of those systems I know is something called AutoDiff Model Builder, which was just used in the fisheries and wildlife, but super cool system. You should check it out. Since then, there's been a lot of different kinds of differentiable probabilistic programming languages. I think of all of these out there, one of the things that who was it? Chris was talking about was the composability of these. And I think I completely agree. I already had it on my slide. Zygote and Turing are by far the most composable ones of these. And something like JAX, but it doesn't have the differentiable probabilistic programming support except through something like Oryx, which I guess we're going to hear something about later. So what is reverse mode autodiff? Let me just remind you what we're doing at the base of STAN. So we're basically converting a STAN program into C++ code, and then we're automatic differentiating, right? So it winds up having a constant cost multiplier for some function on top of actually computing the function itself. The forward pass of reverse mode autodiff, you just evaluate the program to construct the expression DAG. So essentially what I did in designing STAN is I started with bugs and said, how am I going to be able to derive a log density from the kind of bug statement? And I just turned each one of those statements into how it contributed to the log density, and then realized I had something that wasn't really a DAG programming language. What happens in the reverse pass is you wind up, once you've built this big expression graphs, you evaluate your whole log density. It might involve loops, all kinds of special functions. In the reverse pass, you propagate derivatives, and you do that in topological order. That is, you come down the graph, the directed acyclic graph, and you always process a node before you process any of its dependent nodes, any of its operands, right? Now, what winds up happening when we do this, right? So my talk, I should have told you ahead of time, is going to be very low level here in terms of computing. What we wind up getting when we propagate the sub-expression derivatives, so the formula I wrote down there is what one step of propagating derivatives look like. You take the derivative with respect to the result, and you propagate by the partial to get the derivative with respect to the operand. The problem is, after we do the forward evaluation, the sub-expression, so we're evaluating the derivative of a function f applied to n arguments. After we've done the forward eval in the natural order, E1 to En wind up being laid out sequentially in memory, right? This winds up destroying our cache locality. So the problem is that efficiency of modern programming heavily depends on keeping your data in cache. It also depends a lot on branch prediction, right? You want to get rid of all the branches in your code if you can, to up to, as much as you can, which is why C++ is so great, because it lets you do that statically. So here's why. I don't know that a lot of people who work at the level of probabilistic programming languages know this, but when you're coding, if you actually get a cache miss, that is, you're trying to work on a number and that number's not sitting in your cache, the cost to getting it from memory is around 150 clock cycles. Not only that, it's that 150 clock cycles, but that kills your optimistic calculations because the CPUs are typically pipelining and calculating ahead. So it's actually worse than it sounds from thinking this is 150 clock cycles, right? So what this talk's going to be about largely is how we can deal with this cache miss problem through some clever programming, which is all pretty typical. This is just going to be putting together some programming language techniques to try to solve this cache problem in a way, and I'll talk a bit about Gaussian processes. So often when we have a probabilistic program, we have a likelihood term, that is the density of y, our observed data, given our parameters theta, and that often decomposes conditionally independently. It doesn't have to be IID data, but almost always the data is conditionally independent given our parameters, right? That's not true in like simple time series models. It's not true in some cases, but generally we have terms that look like this. The map function, map is a higher order programming language construction. If you take a function f and you map it over some vector v, what you get is the element-wise application of f to each element of that vector, right? What Stan does is it provides this very convenient function called reduce sum. Reduce sum takes a function f, it takes some values y, and then it takes a bunch of parameters theta 1 to theta k, and it computes basically this summation. So it's kind of tailor-made for computing these kinds of map reduce style likelihoods. That is, we do the map to compute the likelihood term, and then we sum them all up. And the nice part about this is we can compress all the derivatives, right? So what happens when we do this? So we're doing a map, and what this does is it reduces to having a bunch of these operations, right? In some sense, those can all be done in parallel, but we don't actually parallelize down to the grain of individual computations because we still want to, on our subprocessors, be able to deal with things like pipelining and SSE and AVX type instructions. So we don't want to kill that by sort of going one observation at a time. So we go blocks of observations at a time. What we do when we have this map function in Stan is we actually do an eager autodiff subgraph evaluation, right? And what this is a kind of runtime form of partial evaluation. So it turns out when we're doing reverse mode autodiff, we can actually evaluate the gradient with respect to some particular sub-expression. So remember, this f is just something that shows up somewhere in the middle of our program. We can actually evaluate its gradients with respect to its inputs anytime after we've evaluated the f. That means we've got the parent node, we can pass it down to the children nodes. Stan does this using nested reverse mode. There's a really clever autodiff system using C++ template programming called adept that does it through forward mode. The nice part about this is it reduces the memory footprint for sub-expressions to order x, right? So what happens is when we build up this complicated function f, it might have all kinds of internal components building up an expression graph. But once we've partially evaluated that, we've evaluated it eagerly, it reduces the memory footprint there. So it has two really good beneficial things. One, it actually lets us evaluate that nested gradient locally. It tends to be much more memory local because we haven't got this big expansive thing across all of our expressions. We're just looking locally. And it increases cache locality in the further upstream operations. So you can think of this as doing like cache local operations, gathering them up, cache local operations, gathering them up, right? What it also allows is parallel evaluation of sub-expression gradients. The way we actually learned that this was happening is we built the parallel version of this. And then we realized even when we weren't running in parallel, that doing this kind of map reduce of our log densities sped up the code as much as like 30 or 40%. And it turns out that's because of cache locality. It's just purely because of memory locality, right? So parallel evaluation is what we did this for. So Stan can either scale up on a single machine using threads, or it can scale out using MPI to multiple machines. All it needs to do for this is communicate the gradients back. This is on the order of the size of the operands, is the amount of information that needs to get computed back and forth. And in the MPI setting, we push data node locally on construction, so we don't have to move data around at runtime. We still have to move parameters back and forth, but data can get pushed out to where it needs to go locally. This is also completely orthogonal to GPU use, in that you can throw on GPUs to do matrix calculations. At the same time, you can parallelize all of this. If F is set up to use GPU computing, then so will this kind of map operations, right? So now let's get to the sort of point of the talk. So Stan, when it's implementing automatic differentiation, it's a templated C++ implementation. What we do is we replace scalar variables in C++ programs like doubles with these autodiff variables, which we just call var in Stan, right? And I didn't quite get the templating right there. That var should have a T template on it in the expression there. But the idea is we use a pointer to implementation to make the encapsulation of resource allocation as initialization. So we basically set this up so it works like standard vectors do in C++. So a var points to a var and a var stores the value of that autodiff variable plus the adjoint. The adjoint during the calculation is going to be the derivative of the final log density value with respect to this particular variable. This immediately gives us two ways to code matrices. So like TensorFlow, we're using eigen to deal with our matrix calculations. So we can either do this two ways. We can take an eigen matrix and we can fill it up with autodiff variables, right? The nice thing about that is it lets us autodiff straight through algorithms that are templated. So this is what let us autodiff straight through eigen's matrix libraries for inverses and solves and determinants and everything like that when we first got started without having to write a lot of custom matrix autodiff, which frankly, we didn't really even understand at that point. The alternative to doing that, right? But the problem with this setup where we make a matrix of autodiff variables is when we calculate matrix derivatives, we usually want to operate on a matrix of double values and an adjoint matrix of double values. And with this matrix of var objects, we have to wind up constructing those submatrices on the fly, which is very expensive because it requires both memory allocation, so it's providing memory pressure, and it's doing a lot of assignment, right? So neither of which are good for throughput. So the alternative way of coding matrices is the other way around. We make an autodiff variable and its type of its value and adjoint is going to be a matrix. This is something we've just introduced recently into Stan, as in like a year or two ago. We had some really great programmers, Tadej Siglarich, who since left the project for industry, did this as like an undergrad and master's student. So you can recruit some really great people for these open source projects. You can get in and like tinker with memory, hook GPUs up. It's amazing. The nice thing about operation B, the second alternative, the var matrix alternative, is that B winds up being memory local for matrix derivatives. That is, we keep the double value, we keep the double adjoints all together, right? The problem is only A supports L value indexing. We can't assign in setup B, we can't easily assign to elements because when we assign to those elements, we wind up breaking locality on those algorithms. We wind up not being able to keep everything together in memory. And everybody thinks they can solve this problem. It's not solvable. We need to go to that second thing. The problem is, what do? We want to use the efficient second form of matrices, but they don't support assignment, right? Well, here's a kind of model that we use an awful lot in Stan, Gaussian processes. It's a non-parametric model, which basically means it has a lot of parameters. So it's like one of the dumber naming conventions. And it acts like a smooth nearest neighbors model. The problem is if I have n observations, I need to construct an n by n covariance matrix sigma. This winds up being big, right? If I have 10,000 observations, this is a big matrix, right? And what I do for each element of that matrix, I define it using a covariance function. So I introduce some function kappa, and given my index I and j, my data x, my parameters theta, it says that this is the covariance. And in the Gaussian process literature, there's dozens of different covariance functions that people use. And in richer models, the sigma winds up being a sum of other covariance matrices. So if I'm doing like a time series model for demand, I might have a weekly trends that go up and down. I might have seasonal trends. I might have overall trends. I might have holidays. I might have a bunch of these covariance matrices pasted together. Right. And the problem is if I explicitly build in covariance matrices and try to add them together just naively using autodiff, it's a complete memory disaster. We can't scale Gaussian processes in Stan at all because of this, right? We're stuck to really data sizes less than 1,000, and we really want to go up to data sizes more than 10,000 or even bigger than that, right? And the bottleneck is just pushing all this stuff into memory. We blow these things up, right? And just building those 10,000 by 10,000 covariance matrices each of which every entry is some complicated function, is just a disaster. It's not that we can't do the computation, it's that we can't fit everything in memory, right? So how are we going to solve this? Well, my suggestion, what we're actually building in Stan, is to use comprehensions. So comprehensions are this concept that was introduced in set theory in the late 1800s, led to Russell's paradox in their unfettered form. They were consistent in ZF set theory in the early 1900s, right? And the idea of a comprehension in set theory is you define a set B as being all the members of A that satisfy some property phi, where phi is just some mapping from A onto Booleans, right? So what we're doing is we're saying, give me all the members of A that solve some property, right? These were introduced into programming languages in the early 1970s and sort of made their way from POP2 all the way up to Python, which is, I think, where they're probably most familiar to people. And we're building them right now for Stan, right? A Python does this for lists. Instead of for sets, they do it in an ordered way. So a Python list comprehension looks like this. I can define some list B by saying, give me the X's for all the X's in A if this condition holds. So it's basically just exactly the list equivalent of this. What we're going to do is we're just going to take this idea of list comprehension, we're going to move that into Stan for matrix comprehension, and we're going to partially evaluate all the derivatives, eagerly evaluate them on the fly, right? So matrix comprehension, what we're doing typically is we're defining this matrix, this covariance matrix this way. We loop over the entries, we define all the entries. If we're being a little clever, we realize it's symmetric and we don't quite do this whole loop, but this is roughly what's going on, right? What happens is Stan's adopting this variadic covariance function style. So it's going to look very much like the way people code GPs in their math papers, where we're going to be able to comprehend a matrix given a function for a bunch of A1s through AN. So I need to actually say N and N there. I'm missing an argument there. There should be two arguments for the sizes N and N there. And then that will build things up basically by using a map underneath, right? This is just a specialized map. We can partially evaluate all the gradients, and we can parallelize and eval the gradients over both of these loops. So we have 100 processors. We can do all these subcomputations in an embarrassingly parallel way. We only then have to merge them back into the big autodiff graph, which is, compared to the amount of work we do on the nodes, really cheap, right? So what happens then for Gaussian processes is this is going to allow us to add covariance functions, right? What's going to happen is here, I guess I should have written this out. Instead of having F, we'll have F plus G plus H plus whatever with a bunch of covariance functions, and then everything gets vectorized underneath and partially evaluated, right? So what we would really like, right, is we would like to be able to have some kind of compiler or runtime automation, right? What I'm suggesting here is something where the user says, oh, I was about to do this really inefficient thing. Maybe I should use this higher order function that does comprehensions because that'll be much more efficient. The reason we want to do this is this doesn't require any assignments to elements of B. When I write this down, this just lets me calculate each one of the elements, right, as this function, and calculate all those partials locally for each one of the elements. Right? This is really painful, right? One of the things I learned over the 10 or 12 years Stan has been going, I was very charmed that somebody said this was the programming language I grew up with, because I often go around and say that about bugs, because I sort of, I wasn't young, but I was using bug well before I got to Stan. So what I learned in doing Stan is most of our users are not programmers. As soon as you have variable declarations, type declarations, and we ask a bunch of applied statisticians to start using indexes, they can't do that. So this is a hard step. This piece I have highlighted for the typical Stan users, this is too much programming. Right, so our high-end users will do it. We'll be able to build packages that exploit this kind of thing. Like we'll be able to write a nice GP package that lets people, a little bit control these things. But most of our mainstream users aren't going to be able to do this. So what we need is we need to get Maria or somebody else back on board who can figure out how to do all the compiler runtime automation. Right, what we want to be able to do is we want to be able to take Stan code that looks like this, right, and turn it into code that looks like this. Right now, conceptually, that looks easy, but Stan allows arbitrary code here. So in general, the problem's undecidable. So there's always some trade-off of where we can go in between. The other thing we want to be able to do with this, as soon as we're starting to parallelize all of this, is we want to be able to do some kind of automatic load balancing. The simple kind of naive mapping, unless you do it at a granularity that's much smaller than the number of cores you have, is very hard to load balance. You're going to set out different jobs on different cores, and they're going to end at different times. And what you're going to wind up doing is just sitting there waiting till the last one gets done. And what you want to do is be able to break things up into smaller blocks, keep the throughput of parallelism going. So we're starting to move over doing that using the Intel thread building blocks on the back end. And I tried to make this talk short. I wanted to get it down to 20 minutes to leave time for questions. So thanks for listening. Here's a couple of references for the Stan language transpiler. So Stan gets converted to C++, and we're writing all that in OCaml now. And then there's the Stan math library, and this is a slightly out of date reference, but it shows how we're actually doing reverse mode autodiff, and it actually shows how we do the autodiff for ODEs and things like that. So I will stop there and take questions.
Awesome talk. Is there any questions?
Thanks, Bob, for the excellent talk. I have a question on one of your slides, which is about the motivation for computing the derivative of a covariance matrix for GP with respect to, say, theta. Is that because we want to optimize theta as some sort of kernel hyperparameter?
Yes, exactly. So what's happening is theta is going to be something like a length scale, doing like automatic relevance detection, or theta is going to be some variance parameter, some hypervariance parameter. Each one of the Gaussian processes is parameterized slightly differently. And right, it might be like the length of the trend, for instance, if we're fitting a trend. Right, and Stan lets you make anything pretty much anywhere a parameter that you can then do inference over. It's not quite as general as something like Turing for letting you do that, but it's pretty close.
Cool. Thanks a lot.
Yeah, and then you can optimize or sample or whatever with it once you've got a differentiable target density.
Maybe I'll ask another question while other people are formulating theirs.
Okay.
How bad is it if we don't have this memory locality? Do you have any benchmarks measuring?
Yeah, the benchmarks is it basically blows out memory on any machine we have access to. So it's pretty bad. It's, it quickly runs up to like terabytes of memory if you start doing this at a large scale. Right, so it's like it's trillions of computations, but that we can do. Terabytes of memory we can't allocate.
Right. Thanks.
I mean, this is also often the problem with at least the original way that bugs was coded, is that scaling it up, because they did an explicit representation of that graph in memory, it became very difficult to scale that because the scale of the graph would go up. So that's one of the things we noticed when we first started doing Stan, is Stan took up much less memory for large scalable problems because we weren't like sort of expanding the program, right? But what happens is that came back and bit us because the autodiff implicitly expands sort of the program underneath. So you wind up facing the same problems no matter what you do.
Cool.
I have a question to previous talk from Martin. So this PDMP approach, as you said in the second last slide or something, this looks like a very nice thing, and so what is the actual roadblock there? Is it that there's too little research yet, or is there something that you still have to figure out, or is it just that we're missing this kind of lighthouse application like Stan is for nuts and bugs was for Gibbs and that kind of thing?
Yeah, it's a good question. The answer is that it's almost all of the work on this is theoretical, and the theoretical work is typically done on this very simplified target distribution, where all the different components are independent and identical, which is theoretically interesting, but in practice not at all the kind of thing that we do when we're really doing MCMC. And it hasn't yet made its way into general purpose software. I mean, currently we've got people working on implementations for specific problems, like problems in genetics and so on. So the issue is, you know, we won't really have an idea of the empirical behavior of these methods until we try and implement them in general purpose software, and then we'll presumably find out in practice if they're, you know, extremely efficient, or if there's some kind of roadblock. I suspect there is a roadblock in many cases. It's just that we don't know yet. I might be overcautious, I don't know, but I'm personally very skeptical of the idea that there is a sort of one-size-fits-all methodology that can solve all target distributions out there. That's just a kind of a philosophical belief, if you like.
Yeah, I can add that Martin's absolutely right. We built Stan. We originally, when we started working on the Stan project, when Andrew Gelman hired me and Matt, we ripped the lid off JAGs and started vectorizing JAGs operations and seeing if we could make Gibbs sampling faster, which I think could be done. But we just quickly ran into problems where Gibbs didn't scale. It wasn't so much that we weren't making it faster. It's just the algorithm doesn't scale because of the reasons you were talking, not the step size reasons, but just because of the conditional independence there. Right. I actually had a question, if I can ask a question of Martin as well, which is, you mentioned somehow that you could figure out what the joint gradient was based on the conditional gradients. Did I hear that correctly? And if so, how?
No, I don't think I said that.
Okay, good. Because I did.
Sorry if you were.
Okay.
So if I misled anybody there, no, okay. I certainly didn't intend to say that.
Okay.
Any final questions for either of the speakers?
There's something in the chat which I will read. To Bob, have you explored any of the recent projects like JAX or DAX? Because the latter claims to be addressing both effect-directed parallel compilation and autodiff.
Sorry, I muted myself. Yes, we've certainly been following JAX. I haven't been following DEX as closely. My understanding is that's a large thing that lets you sort of easily manipulate index structures. So it's like an alternative to using the like tensor representations that people are using now. I may have that wrong though, right? I was just talking to Dave Duvino, who said he's been working on it. So yes, both of those things address it, but again, they address it in a way where you have to write the code in the right way to do that, right? It's not like there's not like a magic thing that can take a Turing equivalent program and figure out how to optimally parallelize it. Right, but certainly, as I was trying to indicate in the talk, I think doing this in something like JAX makes all these pieces much more composable. Right, it makes their architecture for autodiff, like the Julia Zygote architecture, is much more composable and much easier to plug together than Stan's autodiff. I mean, our autodiff's easy to plug together in C++, but we have to push it through our language, which is like 2 steps, which makes it more challenging.
Thanks for the answer, Bob. Great talk.